Here I'm going to be looking at applications of differentiation. In particular, looking at how to use differentiation to help us to sketch graphs and to solve some problems involving functions. Typically what we're asked to do is we're asked to find the local maximum or local minimum of a function. And we know that we can represent the functions as curves, either quadratic or cubic, depending on the type of function. So we can use calculus to try and get a better idea of the maximum or minimum of those functions. So I'm going to start by drawing a curve of a random quadratic equation, and we're going to talk about the slope of that curve. So the curve I've drawn here is just a random quadratic. F of x is equal to ax squared plus bx plus c. In this case, a will be a negative number because the parabola has this shape. So a few things that we know from algebra. Well, from algebra, if we're able to factorize that quadratic, we're then able to find the roots. The roots are the points at which it touches the x-axis. And then from looking at the previous calculus videos, we know that for any quadratic, we're able to get the slope at any point by performing differentiation, i.e. finding the derivative of the function and then plugging in any appropriate value of x, and that will give us the slope at that x point. So I've just moved the curve there just to get a better look at what this function might actually look like. We know that if we factorize the quadratic, we can get the roots. So looking at that quadratic equation, we can actually put values in now. The roots look like it touches at -1 and +4, so then I can use the roots to form the factors, and I can multiply the two factors together, and that will give me the original quadratic. I'm just going to do that quickly. If the roots are -1 and +4, then the factors become x plus 1 and x minus 4. If I multiply that together, I get the quadratic equation x squared minus 3x minus 4. One thing about this function is because the parabola is shaped like that, we know that a is negative, so we actually need to multiply it all by -1, so the actual quadratic equation becomes minus x squared plus 3x plus 4. That is quadratic. That relates to the orange function there. Things I can do with that then, I can find the slope at any point if I derive the function, so I'm just going to find the derivative. F prime x is equal to minus 2x plus 3, and that should allow me to find the slope at any point x. So if I say x is -1, we can find the slope f prime x, which is going to be -2 by -1 plus 3, so that's going to be equal to 5. So I know the slope at that point is +5, so the tangent to the graph will have a slope of +5, so it will look something like this. Now if I have a closer look at x equal to 0, we can see that f prime x becomes -2 times 0 plus 3, which is equal to 3. So we can see what's happening here. As I move throughout the curve, the gradient of the tangent at the point is becoming less steep. So if I check here at x equal to +1, for example, at that point, the slope of the tangent to the curve is 1. So if I draw that in here, we can see that the slope of that tangent is less steep than the slope of the red tangent, which is less steep than the purple tangent. So what's happening to our tangents are becoming more and more horizontal. They're flattening out. So we can now have a look and see what happens at x equals to 2, 3 and 4. What I've done here is I've just plugged in values of x for 2, 3 and 4 into my derivative, and what that has turned out is the slope at those points. So the light blue line here is a negative slope of -1. Then when I move on to the yellow line here, you can see that's a more negative slope again of -3, and then this pink line is a slope of -5 at x equal to 4. So differentiation allows us to find the slope of the tangent to a curve at any point on the curve. Well, the reason we're doing this is, as I said at the beginning, is to try and find the local minimum and the local maximum. As you can see on this curve here, on going from all of these slopes on this side to the slopes on this side, what has happened is I've gone from a positive slope, strongly positive slope, to a less positive slope, all the way through to a less negative slope to a strongly negative slope here in pink. So what must have happened is that slope must have gone through 0, i.e. you must have had a horizontal line. So the tangent to the curve at either the maximum or the minimum of the curve will be horizontal. That means the slope of that will be 0. So just looking at that green line again, I know the slope of that is 0. So what I can do is, if this is my derivative, f prime x, and I've worked that out by using differentiation. If I let that slope equal to 0, so minus 2x plus 3 equal to 0, and I solve for x, by solving for x, I've found the value of x where the tangent to the curve is horizontal, i.e. the tangent to the curve has a slope of 0, which must be either the top of the curve or very bottom of the curve, depending on what type of curve it is. So in this particular case, that point there is where the local maximum occurs, because dy dx was equal to 0, or in this case I just wrote it as f prime x equal to 0. So this is where calculus becomes really useful to finding information about functions. We can find the maximum value of the function or the minimum value of the function always, no matter what the function is, by just deriving the function and letting that derivative equal to 0 and solving for that particular value of x. This is the value of x which had a slope of 0. So in this case it was the local maximum. To find the original y value of that, you would need to just plug that into the original function there, and you get the corresponding y value.